Hello, dear participants and guests of the conference. Nice to see you at this topic. My name is Vikolov Alexei, an associate professor from Moscow Aviation Institute, Russia. Let's appreciate organizing committee for a chance to feel free at this meeting. My topic today is modeling and identification of a mathematical model of high temperature superconducting coil, and I've divided my presentation into 6 sections. First of all, I'm going to point what the purpose, the object, and the subject of the investigation are. Secondly, I'd like to pay your attention to the two-model method. Then I show you 3D CAE model of the high temperature superconductive coil. After that, I inform you of the results of the identification of the lumped parameter model and draw out the conclusions. As I'm recording this topic now, unfortunately, I cannot answer your questions at the end of the presentation. I'm sorry. So let's get started. The purpose of the work is to define thermophysical properties of a high temperature superconducting material, which is used as a coil. You can see it in figure 1. As a coil belonging to an electric generator stator construction. The purpose is achieved by the theoretical experimental method using identification and other problems. They are the next: formulation of identification problem of heat transfer mathematical models with different number of space dimensions. OD is a lumped parameter model, 3D is CAE model. The CAE model is the main, and it is identified with the two-model method on the simplified lumped parameter model. Working out algorithms of identification of the intermediate model and refining the 3D model on the intermediate one. Planning heat physics tests to solve the identification problem. Modeling test regimes using the base model and the intermediate model. The object of the investigation is the dimension and dimensionless models its identification and regularization algorithms. From the object, we extract out the subject of investigation as the algorithms of identification of the models, describing the heat transfer in the composite material of the stator coil and its frame, as well as the properties of those materials as the elements of sequences the iteration process converges to. In the two-model method, we have one of them. It's usually a distributed parameter model, but it might be also a lumped parameter model to be refined, while the second a lumped parameter model matches the first one, identifying its properties dependent on the time or temperature. Then we have to identify the intermediate model twice. First time we identified by the detailed model. Second time we do that by a test prototype. In both cases, reagents need to be the same. It results in that an identified function of the detailed model is expressed by the product of a non-identified function of that model and the quotient of the corresponding function of the intermediate model identified by a prototype, by the one hand, and by the detailed model on the other hand. You can see that in figure 2. The detailed model consisting of 3 elements. Like that in figure 1, has the properties defined in the first approach. The coordinates of the nodes corresponding to those of the intermediate lumped parameter model are shown in table 1. The upper and lower surfaces of the frame, upper and lower surfaces, have the normal in the direction Z. And they do not have a heat transfer as they are insulated thermally to supply better approach to 1D distribution. Of the heat flow through the wall in the direction Z. I'm sorry, according to this figure, normal of the upper and lower surfaces is in the direction Y, plus Y and minus Y. And taking these into account, we have modeled with the heat tests to identify the properties of the materials of the frame, polyamide, and the coil. The first test with duration of 20 minutes is cooling in the outer surfaces with the normal parallel to the plane XZ by boiling liquid nitrogen. The second test with duration of 180 minutes is heating by atmospheric air at the normal state with the temperature equal to 20 Celsius degree. Distribution in the time of the node temperatures of the detailed CAE model matching the nodes of the intermediate lumped parameter model is shown in Figure 3, while space distribution of these at a time instant is shown in figures 4 and 5. Figure 4 for cooling and figure 5 for heating regime. The lumped parameter model is assigned to a part of the CAE model. We identify lumped parameter model by CAE model on the one hand and by an experiment on the other hand. Then we are able to make the CAE model more exact, applying to its properties multipliers equal to the quotients of the coefficients of lumped parameter model identified by experimental regimes and those by CAE model. As a rule, values of thermophysical properties of materials at 20 Celsius degree are known and well as a first approach to the functions. Firstly, from the time of cooling or heating regime and then from the temperature. Having a calculated regime before a current one, we can take properties values at the end of the first regime as the start approach for the second, supplying the continuity of the properties distributions in the time. The distribution of the temperature of the nodes in the lumped parameter model identified by the CAE model is shown in Figure 6. While the dependencies of the heat diffusivities from the temperature are in Figure 7. With this data, we calculate the coefficients with the thermophysical properties of the CAE model are to be multiplied by. Thus, here we can see results for the nodes of lambda parameter model 0, 1, 2, 3, 4. So let's it wrap up. Promising electric power generators and related systems for the transmission of electric current are based on high-temperature superconductors, which nevertheless operate at cryogenic temperatures. The phenomenon of superconductivity takes place in a strictly defined temperature range. Therefore, it depends on the thermal properties, namely thermal conductivity and heat capacity. The identification of the properties of a detailed mathematical model with a dense volumetric or surface mesh is hampered by a large number of nodes and related equations. Therefore, it's advisable to use the two-model method, matching the simplified model to the main one. The simplified model can be one-dimensional or lumped parameter. To develop identification algorithms, there is no need to conduct a full-scale experiment. The simplified model is identified by the result of a virtual experiment that reproduces real conditions. Thus, design calculations of the experiment can be carried out even with unknown material properties. The simplified model is identified by experimental data and the temperature dependencies of its properties, determined by the virtual and real models. For each temperature, a coefficient is found that is equal to the quotient of the properties identified by two models. Detailed and intermediate models have been developed for the stator coil of an high-temperature superconducting generator, which is designed for use in an experimental cryogenic power system of automatic spacecraft. The design calculations of the experiment are carried out according to which a simplified model of coil is identified. So, well, I said you all I wanted to. And if you have any questions, please don't hesitate to ask me by mail. If you haven't, then thank you for your attention and goodbye.